now a postdoc at Ohio State. And Michael did his undergrad studies at MIT, and then finished his PhD under the supervision of Wayne Wu in Chicago, and today he will be telling us about new frontiers of cosmic acceleration.
Okay, so if you squint at this for a minute, you may recognize it as a map of North America. Obviously, it's a little old. It's old, around 400 years old. And, sorry?
I just looked at the North Sea right there.
Yeah, it's North Sea. So there are a couple of features on here that are correct. A few things that are not so correct. But I want to think of this now as a representation of the unknown territory of cosmic acceleration. And so just like the state of European knowledge of North America 400 years ago, we're at a point in time now where we've had some pioneering explorations of the accelerated expansion of the universe using various techniques. And those have provided us with sort of a basic map with some of the main features identified. For example, we know that things look roughly consistent with a cosmological constant, at least over a certain range of redshifts and a certain range of length scales. But there are several other types of theories that are consistent with the data that we have right now, including theories of dynamical dark energy, or theories where gravity is modified on large scales. And so what we'd like to do is try to refine this map and get something that's more like the current map of North America that we have on Google Maps, where you can zoom way out and see the entire continent, zoom all the way in and find the nearest coffee shop. And in order to do that, fortunately we have several different methods at our disposal. And we can think of those as being analogous to different types of vehicles that you might use to explore this terrain. And so each of these different vehicles, probes of acceleration, can take its own unique path through this landscape and allow us to see different features. And so if we want to get the most complete picture of cosmic acceleration and really identify what's causing it, I would argue that we need to combine as many of these different techniques as we possibly can. So about almost 2 years ago now, David Weinberg at Ohio State and myself started discussing doing a review where we look back at the progress so far in the field of cosmic acceleration studies over the past 10 to 15 years, and try to use what we've learned from those experiences to plot out the next decade or so, and figure out which techniques should we try to use, what new techniques might be useful. And so we had a few main goals in this review. One was to try to collect together some of the wisdom that various experts in different observational probes of acceleration have acquired through their experiences. Because there are a lot of very useful facts that are known to a handful of people, but it would be good to make those more widely known as we go forward. We also wanted to make a new set of forecasts looking at the combination of different probes in a consistent way, where we use a unified set of assumptions for the different probes, and then look at variations of those assumptions to see how robust the forecasts are to those assumptions. And finally, we just wanted to provide an updated reference on dark energy and quantum gravity studies from an observational point of view that we hope will be useful for students and researchers. And so in order to address these different goals, we first assembled a team of experts on what we think are the main probes of cosmic acceleration for the next decade. The part of this effort that I was mainly involved in was forecasts, and so there I was running a large number of Fisher matrix analyses covering a range of possible scenarios for these future experiments. And we've put all this together in an article called Observational Probes of Cosmic Acceleration. So besides David and myself, the other authors are Daniel Eisenstein, who brings his knowledge of baryon acoustic oscillations, Chris Rada for weak lensing, Adam Rees for type 1 supernovae, Eduardo Rosso for galaxy clusters. And I'm very happy to be able to actually give you a reference for this now. Everyone I've talked about this before, I've just promised it's coming soon, it's coming soon. So now you can find it on the archive as of last week. And we've already gotten some useful comments from a number of people, but we can always use more feedback. So I would ask you to please, if you have any interest in this, take a look at your favorite section, or want to just skip to the references and see if it's excited you. And but please send us your comments if you have any. And our goal is to take all the comments that we've gotten by this arbitrary deadline, February 17th, so we have a few weeks. And so we'll incorporate those and an updated version of this article that we intend to submit to physics reports. So in the rest of the talk, I want to just focus on some of the main results from these forecasts and just give you some of the highlights from the review. And the main conclusion that we've gotten from this study is that, as has been true in the past, a combination of several different probes to dark energy and modified gravity will continue to be very important to understand cosmic acceleration. So it's not the case that as we improve the precision in all these different methods we have, it's not true that one of these methods is going to tell us everything that we want to know and that we can just focus on that and ignore everything else. We're really going to have to take more of a balanced approach and try to make large improvements in several methods at the same time, especially if we want to go beyond just assuming the simplest model and actually test several different models. On the other hand, that doesn't mean that we should just take every method that anyone has thought of and try to do everything at the same time. We do know that some methods have greater potential than others, and so we should really focus on those and try very hard to reduce the systematic errors so that we can take advantage of those methods. So these are the main points that I want to cover. First, I'll just give an overview of the main observational probes that we considered, remind you of what things they constrain, and then just list various challenges that these probes face. I won't be able to go into them in detail, but there's obviously more information on that in the review article. Then I'll describe the fiducial program that we outlined for what we envision as the path to exploring cosmic acceleration over the next 10 to 20 years. And I'll describe how the parameter constraints change as we vary the assumptions that go into that fiducial program. Then I'll describe how the parameter constraints depend on the assumed cosmological model as we change our assumptions about dark energy or gravity. And finally, I'll discuss a couple of additional probes of cosmic acceleration that we didn't include in this main analysis because it's at present more difficult to forecast how well they'll do. So what are the parameters that we want to measure? Well, the main things I'm going to focus on here are two parameters describing the expansion history of the universe. So this is just the usual W0 WA model. It's linear in scale factor. And you can also write this in terms of WA and WP, which is just shifting this value from redshift 0 up to some fitted redshift ZP. And the reason for doing that is that it makes these two parameters uncorrelated, whereas W0 and WA are highly correlated with each other. And if we were just going to assume that acceleration is caused by some form of dark energy, then WZ is all that we need to measure. But we'd also like to try to figure out whether dark energy is responsible for driving the accelerated expansion, or whether the acceleration is due to some modification of gravity. And so in general, the way that we can do that is by also measuring the growth of structure and checking whether the growth of structure is consistent with what we would predict from the expansion history in the context of general relativity. So we have two additional parameters for growth. The usual growth function is g sub gr of c, and then we modify that with a constant factor g9, which just rescales the overall amplitude of growth at high redshift. And then we have the parameter delta gamma, and that changes the differential growth rate So you may be familiar with the approximation that the growth rate, which I'm calling here F sub GR of C, can be well approximated in the context of general relativity as omega m of z to the power of gamma, where gamma is approximately equal to 0.55. And so this delta gamma parameter just describes some small deviation from that 0.55 estimate. So those are the two growth parameters that we'll include to look for possible deviations from the yard. And this parameterization is inspired by the Degree Merit Science Working Group report from a few years ago. So the first probe I'll talk about is type 1a supernovae. So just to remind you, the main thing that we're measuring there is the apparent magnitudes of supernovae at different redshifts, and then comparing the magnitudes of the supernovae under the assumption that they have the same intrinsic magnitude, or that we can at least correct them using properties of their light curves and colors and so on, so that they are basically standard candles. We can compare these magnitudes to infer the ratios of the luminosity distances to supernovae at different redshifts, and then that allows us to infer constraints on the V of Z. So this is an example of the current state of the supernova measurements. There are several different compilations of supernovae right now. Here I've just taken the Union 2 compilation, which consists of 557 type 1a supernovae observed with a variety of instruments. And so the luminosity distance versus redshift is shown as the gray points here, and I've plotted over that a flat CDM model, and so you can see that that model is very consistent with the supernova data. The bottom panel is just showing the directional deviations, and the colored lines here are showing a couple of other alternative models of flat CDM varying the spatial curvature by plus or minus 0.01, or varying the equation of state W by 0.1.
So the lower graph, so 1%, if delta DL over DL is about 1%, then you get 50. That's roughly the difference between the small pieces.
Sorry, 1% would be pretty small. That's obviously.
No, I mean all lines seem like very close. So that's why I asked
right.
What's the difference.
So it's hard to see because there's so much scattered gray points, over 500 points here. So these open circles here are showing averages in bins with 0.2, I think. So you can see that there that is consistent with the black line, and you can sort of imagine that it allows you to distinguish maybe the one signal between some of these other possibilities. But these deviations are actually somewhat small, given the current constraints right now. It's sort of one single level or slightly smaller. So as we move forward with future type 1a supernova surveys, some of the main things that we're going to have to worry about, and these are actually some of the limiting systematics for current surveys, are the ability to calibrate the flux accurately between supernova samples at very different redshifts. So it's one of the main challenges, because obviously we can't calibrate the flux and we can't accurately determine their magnitudes. We also have to worry about uncertainties related to dust extinction and how that affects the colors and magnitudes of supernovae. It's been suggested that one way in the future we're trying to get around this in some degrees to make observations of the supernovae in the rest frame infrared, where they should be less affected by dust. And then another systematic that could affect supernova constraints is the possibility of evolution of the properties of the supernova. So for example, if the supernovae are made up of two different populations that have different progenitors, and those populations have slightly different relations between their intrinsic magnitude and the shape of the light curve or the colors, then if the fraction in each of those populations changes with time, then that could end up biasing the supernova constraints. So considering all of these systematic errors, we've come up with a set of stage 4 forecast assumptions. And stage 4 here is using the language of the Dark Energy Task Force report from a few years ago, which at the time said, stage 2 experiments were the ones that were going on now. Basically, those have been completed now by now. Stage 3, at the time of DTF, were the next generation of experiments, which are basically the experiments that are starting about now or about to start in 1 or 2 years. For example, things like the Supernovae survey or the Variant Oscillation Spectroscopic survey in Sloan 3. And so the stage 4 experiments that I'm talking about here are the things that are currently being proposed for the next decade. Experiments like LSST, Big Boss, and space missions like Euclid and the universe. So our main forecast for the supernovae for stage 4 was to take 3 bins in redshift with delta z equals 0.2 from 0.2 to 0.8, and assume that the total errors, so that's including statistical and systematic errors, in each of those bins can get down to 0.01 magnitudes. Now this would likely be limited by the systematic errors because given the intrinsic scatter in supernovae of about 0.15, you'd only need a sample of about 1,000 supernovae to get down to this level in terms of statistical errors, and currently planned surveys, or surveys in progress, are already collecting thousands of supernovae. So getting down to this level of statistical errors should be easy, and the challenge is really getting the systematics down to this level. Then we also include a local sample for calibration. As I said, we're measuring relative distances with supernovae, and so it helps to have a low redshift sample, so we include one at redshift of 0.05, assuming the same 0.01 magnitude error. Moving on to baryon acoustic oscillations. These provide us with a standard ruler that's calibrated to the cosmic microwave background, and we can measure that scale in the clustering of galaxies or other tracers of matter distribution. If we measure the scale in the transverse clustering, that tells us the angular diameter distance to that redshift, and if we measure it in radial line-of-sight clustering, then that tells us the expansion rate, h of z, directly. And so using both of these gives us constraints on the z. So this plot is summarizing the current state of the VAO measurements. And so far, the statistics haven't been good enough to really do this separation into transverse and radial constraints. And so instead, the current experimental constraints in combination is called dB of z, basically the monopole measurement. And there are constraints, independent constraints at 3 different redshifts currently. So there's a low redshift measurement from the 6DF galaxy survey, measurement around redshift 0.25 coming from Sloan 2 plus the 2DF galaxy redshift survey, and then measurement at higher redshifts from the Wiggles survey. And again, the curve is showing the predictions of a flat line CDM model, and it's nicely consistent with all the measurements that we have so far. So what are some of the systematics that people are working about for future VAO measurements? Well, basically, you have to worry about anything that might shift the position of this baryon oscillation peak in the correlation function or in the power spectrum. And so one concern is the effects of the nonlinear growth of structure as you go to lower redshifts. So it's been shown that that can shift the peak by a small amount, but for the most part, that just tends to broaden out the VAO feature without moving it significantly. There are also concerns about the effects of galaxy bias, because what we can predict most easily is the clustering of dark matter, but what we measure are tracers like galaxies, and so if those tracers are not perfectly mapping out the clustering of dark matter, then there can be some systematic differences. So both of those have been studied using simulations and perturbation theory, and there are small shifts that have been identified that it seems possible to correct those using methods that use the Zeldovich approximation to try to undo the effects of nonlinear growth. Redshift space distortions are another concern. We want to separate out the information in the transverse and radial directions. So you have to be able to model the effects of particular velocities there. And then there are other techniques that have been proposed to measure variant acoustic oscillations that have their own systematics that belong with them. So for example, the BOSS survey is currently working on measurements of VAO using line alpha forests in spectra of quasars. And so one of the issues there is how well you can model the continuum of emission from the quasars to subtract that out. Also, there are ideas about using 21 centimeter observations for VAO, and as I'm sure sort of what you know, the challenge for that is the ability to remove forevariance. So for variant acoustic oscillations, the assumptions we made for our stage 4 forecast are that you have measurements over a quarter of the sky going out to redshift 3. And we've taken the errors that you get in the limit of sample variance and just multiplied those by a factor of 1.8. And this is calibrated in order to account for the effects of actually having finite sampling of this volume out to redshift 3, and also to account for the reconstruction techniques to remove nonlinear effects. Now, weak lensing gives us a different probe of cosmic acceleration by looking for correlations in the shapes of distant background galaxies that have their images sheared by foreground matter distribution. And so unlike the Supernovae and VAO techniques, this gives us a unique probe of acceleration because it's sensitive to the growth of structure, because it depends on the amount of fluctuations in matter in front of these background galaxies. Also, the strength of weak lensing signal is sensitive to the distances to the lenses and sources, and so weak lensing also provides us information about distances. So combined, we can get information from weak lensing on WZ. We can also constrain this perturbation to the growth rate delta gamma. And if we compare the growth measurement from weak lensing with the measurement of growth from the CMD, which I'll mention in a minute, then that can give us constraint on this normalization of the growth of G9. So this is an example of the current weak lensing constraints. This is coming from the HSC Cosmos survey, and it's showing the correlation function in E modes and B modes. So generally, we expect the cosmic shear signal to only have an E mode component and to be the 0 B modes. So far, weak lensing has not progressed to the point where it would significantly constrains WZ. And typically, the current measurements are expressed in terms of a combination of the amplitude of downward clustering sigma 8 and omega m to some power, which is usually around 0.4, 0.7. And present uncertainty from several different surveys on this quantity is about 0.05 to 0.1. So given that sigma 8 is around 0.8, this is something like a 10% measurement.
And the lines, what are the lines of the graph? The forecast or system?
So I think the different dashed lines going through the points are just testing the effect of
No, the solid.
the solid lines. I'm not sure. I'd have to go back and look at the paper. I would guess the solid lines are representing their theoretical prediction for the flat notes in the model, and some maybe some points of the range of that. So in order to advance weak lensing to the point where it can give us very strong constraints on WC and growth parameters, there are several systematics that need to be dealt with. One is that we need to be able to accurately measure the shapes of the background galaxies. And so that requires both accurately estimating and correcting for the point spread function in the observations, and also making sure that the shape measurement algorithms are unbiased. Another important systematic is uncertainties in the distribution of the redshifts of the source galaxies. Also, intrinsic alignments are a concern. So for cosmic shear measurements, the standard assumption is that the shear signal is only coming from gravitational lensing, but in practice, we expect that there are actually some intrinsic correlations between the shapes of the galaxies, just due to the fact that they're sitting in some tidal field, which causes shapes at a similar redshift to be correlated, or which can correlate the orientation of the foreground galaxy with the shear of the background galaxy. And so these intrinsic alignment effects are important to model or to try to remove from the data in some way. And another possible source of error are uncertainties in predictions of the matter power spectrum. So the power of weak lensing is greatest on small scales, but that's also where these predictions are most uncertain because of nonlinearities and the effects of baryons on cluster matter. So there's a lot of work to do with simulations to try to make more accurate predictions. So our stage 4 forecast assumptions for weak lensing, as for the BAO forecasts, we assume the quarter of the sky and density of 23 galaxies per square arc minute, which is likely to require some sort of space-based observations. We assumed a median redshift of 0.84 for the source galaxies. And we concluded in the forecast not only the shear-shear autocorrelation, but also the autocorrelation of galaxies and the cross-correlation between the two. And then we marginalize over a model of intrinsic alignments and consider total errors in shear calibration and the mean photometric redshift of the source galaxies with an RMS of 2 times 10 minus 3. Finally, cosmic microwave background is often not thought of as proto-dark energy specifically, but it does give us a lot of information that's very useful in constraining dark energy for modified gravity models. One is that the measurement of the acoustic scale in the CMB tells us the distance to a redshift of 1100, and so that helps constrain the equation of state and spatial curvature. You can also measure the acoustic peak heights to infer the growth normalization, which, as I mentioned earlier, can be compared with some low redshift measurement growth to get constrained on this G9 parameter. We can also measure the matter density and baryon density from the acoustic peak heights, and that's particularly important for the BAO technique, since if we know the matter and baryon densities, we can compute the sound horizon, which is required to calibrate the BAO scale. And then there's also additional information in the forms of secondary anisotropies of the CMB, things like the integrated Sachs-Wolf effect, the Sunyaev-Zeldovich effect, lensing of the CMB. And since those are coming from lower redshifts, they potentially give a more direct probe of physics of cosmic acceleration. Okay, so now I want to put these 4 different observational probes together, taking our fiducial stage 4 assumptions, and look at what the expected parameter uncertainties are coming from this fiducial program, and then look at some variations of those assumptions and see how that affects the parameter uncertainties. So as I mentioned before, we're doing Fisher-Maker's forecasts, so we have to assume some fiducial model, which we simplicate to be spatially flat minus EM with general relativity. And in that case, the marginalized once-again errors for these 4 parameters that we get in the stage 4 forecasts are 0.01 for the pivot value of W, 0.1 for WA. In general, WA errors are about 10 times those of WP. We get an error of 0.03 for delta gamma, and about a 2% measurement of G9. So we can compare those to some forecasts for the stage 3 probes and to an approximation of concurrent constraints. And we see that compared to our current knowledge of these parameters, we expect to get for stage 4 roughly an order of magnitude improvement in each of these parameters individually. And just to note, the pivot redshift for WP for stage 4 is about 0.5, and for the other cases, it's a slightly lower redshift. So So now I want to look at some variations of these standard assumptions. And so to do that, we take the total Fisher matrix, which is some of the CVs, Supernova, BAO, Lensing Fisher matrices, and then just put some coefficient in front of each of these three terms and allow that to vary from 1 to rescale the total errors of each of these Supernova, BAO, Lensing constraints individually or together. So I'm going to keep the CMB component as fixed. We're just assuming for these forecasts that comes from the expected performance of the Planck mission, and that seems to be relatively well defined, so we just know that as it is. So for example, if we wanted to scale the BAO errors while keeping everything else the same, we can look at half the errors by taking C2 equals 4, and so on, with twice the errors, 4 times the errors. So these are 1 sigma contours for the W parameters. Here instead of WP, I'm writing W.5, but as I mentioned, pivot redshift for stage 4 is close to 0.5. So this value of W is equals 0.5 is similar to WP. And on the right, I'm showing constraints on delta gamma and log G9 as I vary the errors of the supernova technique. The blue ellipses are showing the standard stage 4 forecasts that we started with, and then the inner black contour shows what happens if you have the supernova errors. The green contour is doubling the supernova errors, and the red contour is 4 times those errors. So you can see that there's a significant effect on the constraints on W as we vary the supernova errors, and so that indicates that the supernovae are contributing quite a bit to the constraints on the expansion history. But there's no variation in the growth constraints, and that's not too surprising because the supernovae are just giving us measurements of distances. They're not directly constraining the growth, and so we wouldn't really expect this to change too much as we change our assumptions for the supernova.
So I can think of the pivot redshift as like the median redshift.
It's basically the redshift where W is constrained best. So this two-parameter W0 WA model, you plot the errors as a function of redshift, you have some neck at a certain redshift where the errors are best, and that's where WP is. That also means those two parameters unfold. But here I'm just fixing it as equals 0.5, so it's not necessarily the redshift. So we can do the same exercise for BAO. So again, blue is the initial assumptions, and then having doubling or quadrupling the errors. And here again, there's not much of an effect on the growth parameters. There's some additional information about G9, which just comes from the fact that the BAO measurements are constraining the equation of state at high redshifts, which allows the genericity between the equation of state and this growth parameter to be broken. But again, the main constraints coming from BAO are in these W.5 and the UA parameters. And an interesting thing to note is that the direction in which these contours change is very different from what we have for the supernova. And so that's indicating a high degree of complementarity between the supernovae, which are mainly constraining the equation of state at low redshifts, and BAO, which is providing better constraints at high redshifts. We look at the same thing for Lensing variations. Now we see the opposite effect, where the changes in the W parameters as we vary weak Lensing errors is fairly small, but there's a huge effect on the errors on delta gamma and log G9. And so again, this is showing that the weak Lensing observations in this program are very complementary to supernovae and BAO because they provide constraint on these growth parameters that the other probes don't provide, and that allows us to potentially find deviations from general relativity. So just to summarize the main conclusions of those variations, supernovae are providing good measurements of W at low redshifts. BAO are better at measuring W at high redshifts. That's partly because BAO is a statistical technique, and so the more volume you have, the more galaxies you can measure. so that improves the constraints. Also, DAO does better at high redshifts because it's able to constrain h of z in addition to distances, and the sensitivity of h of z becomes much greater. The sensitivity of h of z to the equation of state variations becomes much greater at high redshift than the sensitivity of distances, which are integrating to the range. And finally, lensing is providing valuable additional information about possible deviations from the DR. So we can ask a couple of other questions looking at different types of variations in these forecasts. And one question that we thought was interesting was whether it's more important to get sort of quality supernova measurements or quantity, which we both mean, is it better to take the same range in redshift for the supernovae and just reduce the errors as much as possible, or should we be trying to push supernova measurements out to as high redshift as possible? So on the left here, I'm just showing the same variations with the supernova errors as I did in the previous contour plots, but here is the constraints on WP and WA are condensed down to this single figure of merit number. So higher figures of merit are better constraints on WP and WA. And so we can see the scaling with supernova errors here. And then on the right, I'm showing how this figure of merit changes as we vary the maximum redshift of the supernovae, assuming the same total error in each bin. So the circle is marking our fiducial choice of 0.8. And you can see that as we vary the maximum redshift, especially as we go to higher redshifts, the scaling of the figure of merit with Zmax is quite a bit shallower than the scaling of the errors. So this is suggesting that given the choice between these two options, it seems more effective to try to reduce the systematic errors in the supernova measurements as much as possible, instead of trying to go to redshifts above 1. Another thing that we looked at was the impact of our assumptions about weak lensing systematics. And so on the left here, I'm showing the same weak lensing supernova and DAO scaling of the figure of merit with each of those errors as I showed in the contour plots. So as we saw before, the scaling of weak lensing observations is very weak because they remain sensitive to the growth of structure parameters, but not to the expansion history. But if we take a more optimistic assumption about the weak lensing systematics, where we just assume that the total errors from weak lensing are twice the statistical errors, then the picture changes quite dramatically. And we see that in this case, for the more optimistic assumptions about the systematics, the weak lensing sensitivity to WP and WA is actually more than supernova and DAO over some ranges, and comparable to the supernovae down here.
So why does the supernova scaling change as well? Sorry, I'm just varying the weak lensing.
So going from here to here, I'm changing our whole weak lensing model of the systematics, and that's added into everything else.
Oh,
so in the red curve, for example, I'm not varying the weak lensing errors, but the Fisher matrix is still represented in one side. So that's why all of the errors change. Okay, so now I want to discuss what happens as we change the cosmological model and go away from this two-parameter assumption for WC or two-parameter assumption for the modified gravity parameters. And so what we find is that, in general, constraints on parameters other than WC depend very strongly on our model for the expansion history. So here I'm comparing three different cases. So the center points are the errors for the W0 WA parameterization. On the left, I'm assuming lambda CDM, W equals -1. And then on the right, I'm showing the errors for a much more general parameterization of WA, where we divide W into 36 bins and scale factors that are allowed to vary independently. And so we can see that as we change the model for WA, the errors for certain parameters, such as omega k and h, vary by orders of magnitude. G9 is also affected Interestingly, the constraints on delta gamma seem to be fairly robust to these changes in the model. And you might wonder what happens as we add additional types of probes, if that would possibly reduce the model dependence of these errors. But it turns out that, for example, if we add clusters to the initial set of forecasts, that reduces the model dependence in the case of the Hubble constant. But for G9 and omega k, it actually slightly increases the model dependence because the addition of Gaussian cluster constraints has more of an impact in the simpler WA parameterizations than it does in this more general case.
Oh, actually, sorry, so the next plot might be the example I was going to about the number of bins.
I'm not sure if it's actually.
Okay, so I'm just wondering what if you 36 bins is a lot. So how does it scale when you reduce the number of bins down? So what is the kind of minimum number of bins where you don't go an order of magnitude?
I don't know. I think it would depend a lot on exactly where you place the bins. It's a small number.
Yeah.
So that's not something we look at in detail.
So obviously like 10 bins between like 0 and 1 that probably tells you more than W0 WA than just W0 WA or something like that.
Right.
Or maybe 10 bins between, but it's obviously a lot less than 36 bins.
Yeah, I'm not sure exactly what that involves. So we can also ask what happens if we, instead of marginalizing over these structure parameters, if we were just to assume GR and fix delta gamma equals 0 and G9 equals 1. And it turns out that that really doesn't have much of an impact on the errors on the other parameters in our standard forecasts. So you can see for WA, WP, H, and omega k, everything is more or less the same as we assume GR or marginalize these parameters. That's true at least for the W0 WA parameterization. If we allow the more general 36-bin parameterization of WA, then the error on H shoots up, but still remains independent of this assumption. But omega k errors do have some dependence on whether we use GR or not. And then finally, we can look in this 36-bin parameterization, how well can we constrain WZ itself? And it turns out that even if we have all of these stage 4 probes combined together, it's very difficult to get any constraints that are useful on WZ in a very general parameterization without putting some sort of strong priors on the models. So this is showing the constraints that we get, or a range of models that are consistent with our stage 4 forecasts using our standard priors, which correspond to putting a Gaussian prior on each of these 36 bins with a width of 10, and assuming that they're uncorrelated in scale factor. And so you get huge deviations here of order. This prior delta W equals 10. And basically this is sort of useless to try to distinguish between different gravity models. And so in order to get some more reasonable set of models, we have to put some very strong prior on the allowed amplitude deviations, here delta W equals 1.6, and also assuming some sort of correlation in redshift or scale factor, restricting models to ones that vary more smoothly with redshift helps as well. So here a correlation of the scale factor of 0.2, and now the deviations are more of the 0.1 level of GC. So this is just something useful to keep in mind that if we want to constrain W itself, we always have to assume that there's some very strong priors on general parameterization like this, or we have to assume some sort of model with these really way. Finally, how much time do we have? 5 minutes. So I just want to make a few comments about some additional pros of cognitive acceleration, which we didn't include along with our main set of forecasts. So one interesting question is how much additional information might we be able to get for measurements of galaxy cluster abundances as a function of mass and redshift. And so the way that we've looked at the information from these additional probes like galaxy clusters is to take our standard forecasts of supernovae, DAO, weak lensing, and C&D, and ask how well those constraints limit the quantity that's best measured by galaxy clusters. And so that is something like sigma 8 of z times omega m to the 0.4. And so if we take our Fisher matrix forecast for these probes and project those onto this quantity, then we get the red curve shown here. So that's telling us that even before we add in clusters, we have constraints on the quantity that they would measure at roughly the 1% level or slightly better. And so that's sort of a target for the cluster measurements to reach in order to have a significant impact on our constraints on the expansion history of the growth structure. So what we've done is to look at our best guess at the actual constraints that we can get from sampled clusters, where we assume that the masses of the clusters are calibrated by using stacked weak lensing observations. And so assuming that we can reach the statistical errors for those mass measurements, going down to some minimum mass threshold of 8, 4, 2, or 1 times 10 to the 14 solar masses, we get the 4 sets of forecasts shown here. And so what we find is that under these somewhat optimistic assumptions about the cluster errors, if we can measure them down to about 4 times 10 to the 14 solar masses or smaller masses, then we should get down to the point where clusters are contributing significantly beyond what we already have from the other probes. So we can look directly at what impact these additional constraints would have by just taking the Fisher matrix for clusters and adding them to everything else. And so these contours are showing what we have without the clusters in the outer red contours for W.5 WA and delta gamma ball G9. And then as we go into the other contours, it's showing the impact of adding clusters going down each of these mass thresholds. And so we find that there's some significant effect on the growth measurements in the clusters. What we were sort of surprised at was how much clusters contributed to the measurements of the expansion history. And we think that's partly because clusters are not only measuring the growth of structure through sigma 8 of z, they're also helping to constrain the matter density, and that is degenerate with W.5 and WA. So removing some of those degeneracies helps to tighten the constraints on the expansion history as well. Another probe that could provide interesting constraints on these parameters is measurements of redshift space distortions. So I mentioned redshift space distortions as a possible systematic for the baryon acoustic oscillation technique. But more generally, you can try to get information out of the redshift space distortions by just looking for the anisotropic pattern of the clustering signal on overall scales, not just at the DAO scale. And so in general, you can write the observed power spectrum for some tracer like galaxies in terms of the matter power spectrum, the growth rate f of z, and the galaxy by speed, and then mu here is the angle between the wave vector k and the line of sight. So this angular dependence of the clustering pattern allows us to get a constraint on this amplitude here, which is proportional to sigma 8 times f squared. So the quantity is mainly measured by redshift space distortions, is sigma 8 times f. We can do the same thing as we did for the clusters and ask what are our predictions for sigma 8 times f coming from our fiducial program of supernovae, DAO, weak lensing, and C&D. And that gives us the solid curve shown here. So we can see that at high redshifts, we already have a fairly good idea of what this quantity is around the 1% level. But as you go down to low redshifts, the uncertainty in growth rate due to delta gamma increases the uncertainty in this quantity quite a bit. However, if we compare this to some forecasts for the accuracy of redshift space distortions from Voss and Euclid, or the 51st, moving from White to Song Percival, we see that those forecast uncertainties are actually even steeper with redshift than what we get from the other probes. And so that means that even though what we'd really like is to have very low redshift measurements to try to reduce this uncertainty, in practice, you're going to get the greatest gains out of higher redshifts, where the greater volume available allows better constraints from reduced space distortions. And so, in the end, if you take these Euclid first forecasts and add those into the forecast we have from the other probes, you go down from constraint on delta gamma of something like 0.03 to 0.04 down to about 0.01. And so this indicates that to the degree that we can believe in these forecasts, redshift space distortions could significantly improve the constraints on the structure and allow us to have a better ability to distinguish between dark energy by gravity. There are also other ideas about how to get more out of combinations of different probes. So in the forecast I've been showing, I've just been simply treating the Fisher matrices of different probes as being completely independent and then adding together their constraints. But we can try to be a little bit more clever than that and use some of the advantages of some probes to cancel out disadvantages for other ones. So if we look again at the effects of redshift space distortions in terms of the actual matter fluctuations instead of power spectrum. So the observed fluctuations of galaxies follow a similar relation to the matter fluctuations. And so the key point is that if we can make these measurements using tracers that have different bias factors here, then these delta observed k for those different biases will have different angular dependencies, but they'll trace the same underlying matter fluctuations delta k. And so if we can make measurements of these different tracers over the same volume and compare them mode by mode instead of comparing the statistical measures of the power spectrum correlation functions, then that offers the possibility of getting improved constraints that are basically free of cosmic variance for this ratio B over F, and also improving measurements of amplitudes that are 8 times F. So this is an idea proposed by McDonald and Seljak. There was a related idea from Libby Penn, which looked at combining redshift space distortions with weak lensing measurements over the same area. And in a similar way, that can give you cosmic variance-free measurements of the bias factors B. And so combining this measurement of B with the measurement of B over F, you can get a constraint just on F of Z by itself without cosmic variance. That also allows you to determine sigma 8 of Z. And so recently, Bernstein and Kai have looked at some forecasts for how well we'd be able to do this separation, and they concluded that using this technique would allow you to basically increase the constraining power on growth measurements in a way that's equivalent to a survey that's as much as 10 times larger. So there are, of course, several challenges to actually implementing this method, dealing with nonlinear effects and stochastic bias, and how to deal with cases where the volumes of these surveys don't necessarily overlap completely. This seems like a promising way of trying to actually do better than you would infer from the simple forecast. And there may be other types of ideas like this that would allow us to do even better than we're doing with this. So just to summarize the main points, first of all, again, please take a look at the review if you're interested and send us comments. So the main conclusions from the forecasts are that this combination of complementary supernova geo with lensing and CB measurements should allow us to improve our constraints on WA and the growth of structure by an order of magnitude over the next decade or so. For supernovae, it seems to be more important to reduce systematic errors at redshifts below 1 than to work on extending supernovae out to redshifts greater than 1. DO constraints on the expansion rate and the angular diameter distance over large volume can give us very powerful constraints on the expansion history. Weak lensing in all of our forecasts is very useful for getting constraints on the growth of structure. Whether or not it provides useful additional constraints on WA depends very much on how much we can reduce the systematic errors in weak lensing. There's strong model dependence for many parameters on the assumed WA model, but whether or not we assume we are marginalized over those parameters seems to have less of an effect It's very difficult to constrain the WBA itself unless we assume some of the parameterization and very strong priors. And additional approach like clusters and R's and Richard space distortions could significantly add to these constraints here. If we can get the systematic errors down to a low level, and we can use some of these multi-tracer techniques. So, just to conclude, as we continue to explore this territory of cosmic acceleration, we may just discover that everything continues to look like the simplest time CDM model. We may find that it looks more like dynamic dark energy or modified gravity, or maybe we'll discover something that we didn't expect.
Questions?
Well, how long will it take to get this back to the thing? Do you need W first?
So W first would definitely help with a lot of these techniques. So it'd be very useful for supernovae, weak cleansing, and during acoustic oscillations, and basically do a lot of this. So if you don't have W first, LSSC will still try to do weak cleansing, so when that happens, Big Boss is working on getting spectroscopic measurements.
But if you are forced to work in ground, what's your off-the-cuff estimate of how much improvement is possible?
Quantitatively, I'm not sure. I don't think we would get to the level of these forecasts necessarily. I mean, hopefully, even if W first doesn't happen, it looks like we could have a good chance of going forward, and that that's not going to do exactly what W first is designed to do, but it would at least help a lot with weak cleansing observations from space. So that's one thing that's very most effective by getting limited to ground-based measurements is that you don't really have the same density of galaxies that you can accurately measure the space. But it would also limit the ability to use the supernova technique if it's actually important to get good infrared measurements, with some of these instruments like clusters.
Questions?
So what are these coefficients that you have? The purpose is what? To assume that, okay, assuming we don't get such good systematic,
Right,
reducing systematic errors, or assuming that.
Yeah, because it's very difficult to know how well these experiments are going to do, how well systematic errors can be reduced, because a lot of it relies on assuming that people are going to think of better ways to measure galaxy shapes and just handle models and those other effects. And so it's basically a fudge factor to put in there to say, you're looking at our forecasts and you say, well, the supernova and the AO assumptions seem reasonable, but I don't believe those weak cleansing forecasts. And you can look at what happens if you increase this or take out the factor to see how that affects the variable constraints. So that was basically the idea. So I showed some limited set of variations, but we have some tables of different cases in the article. The idea is that people can sort of work out what they think are most plausible.
I guess we can stop here and go out for cookies. Mike is going to be here until Wednesday, and let's thank you back again.
Today is Monday. Today is accused by